In our previous lecture, we started our discussion on process instrumentation part of the course Process Control and Instrumentation. Today, let's start with a brief review of what you learned in previous lecture. We started with general principles of measurement systems. We gave a very brief introduction to measurement systems. We talked about purpose of measurement, types of measurement applications, direct measurements versus indirect measurement, functions of an instrument. Then we introduced a concept called functional elements of an instrument. We defined what are the functional elements. We also talked about two different schemes which you can use to break down an instrument into its various functional elements. So, today we will take an example now to understand better how to break down an instrument into its various functional elements. We talked about this scheme in our previous lecture. This block diagram represents the all possible functional elements that you can expect to see in an instrument if you want to analyze it. This is the process or measuring medium. We call this measurand. So, the first functional element, which is called primary sensing element, interacts with the measuring medium first and receives information about the measured quantity and produces an output which is somewhere related to the input to the primary sensing element that comes from the measuring medium. Then we have variable conversion element, which can convert the physical nature of the output signal from the primary sensing element if it is required for the purpose of measurement. So, this output signal can be different from this input signal. Then, if it is necessary to magnify the magnitude of this signal, we can have a variable manipulation element next. Then, if the different parts of the instruments are separated by a distance, we need to transmit data from one point to another. So, we have a data transmission element which will transmit data from one point to another. Then finally, we will have an element which will present the data in a recognizable form to the observer. So, we have a data presentation element. Before we take an example and break down the instrument into its various functional elements, let us trace on the following points. These represent a possible arrangement of all the functional elements that is necessary to describe the operation of an instrument. Remember, we are talking about functional elements, not physical elements. In this block diagram, it is shown that this primary sensing element, variable conversion element and all these elements are separated into separate blocks. Instruments are in general not separated into such blocks. Instruments may involve the basic functions in any number and any combinations. So, let us take an example of pressure thermometer. So, this is an instrument used for measurement of temperature. You have a bulb here, then a tube is connected to the bulb and the other end of the tube goes to a pressure measuring element. What you see from here is just the pointer and the scale. The bulb and the entire tube is filled with a liquid called filling liquid. Now, let us see the part which we can't see. This is the pressure thermometer, and this is what it will look like if you get to see what is inside this. You have a bulb here, the same bulb. The bulb is connected to a tube or capillary tube. To other end of the tube, a boron tube is attached. It may be a spiral boron tube or it may be a C boron tube. We will see what a boron tube is in few minutes. Then the other end of the boron tube or the free end of the boron tube is connected to a pointer and scale through some gear and linkage mechanism. So, before we analyze how this instrument works, let us see what a boron tube is. We take a tube with circular cross section. Then flatten the tube to change the cross section of the tube from circular to elliptical. And then seal one end of the tube and finally bend the tube in the form of a C. This is called boron tube. Named after its inventor. Now, if I keep this end of the boron tube rigidly fixed and apply a fluid pressure inside the boron tube, the tip of the boron tube will deflect. This is boron tube tip. Now, the tip deflection depends on various factors such as the material of construction of the boron tube, usually metals with good elastic properties chosen. It depends on the angle through which it is bent. It depends on its cross section, but most importantly, it depends on the amount of pressure that is being applied inside the boron tube. So, for a given boron tube, the deflection of the tip can be directly related to the pressure that is being applied inside the boron tube. So, for a given boron tube, the tip deflection is proportional to the pressure being applied. So, if through some gear and linkage mechanism I can attach a pointer and scale, the deflection of the pointer over this scale can be directly taken as a measure of the boron tube pressure. So, the scale can be directly calibrated in terms of pressure units. So, the deflection of the tip of the Bourdon tube, which is magnified by this pointer, can be considered as a measure of the pressure. Now, let us come to our previous example to analyze how we can break down this pressure thermometer into its various functional elements. So, this is the bulb of the pressure thermometer. Next, a capillary tube which is connected to a Bourdon tube, which is not bent in the form of a C, but it is a spiral Bourdon tube. The spiral Bourdon tube is chosen here because the tip deflection even further increases if we take a spiral type Bourdon tube instead of a C type Bourdon tube. So, we essentially increase the sensitivity of the Bourdon tube by converting it from a C type Bourdon tube to a spiral type Bourdon tube. Now, this entire part of the bulb, the capillary tube and the inside of the spiral Bourdon tube is filled with a liquid called filling liquid. In certain applications, it can also be filled with gas. Now, this bulb is put into the medium whose temperature I want to measure. So, bulb receives thermal energy from the medium and the filling liquid inside the bulb expands. Now, due to restricted thermal expansion of the filling liquid, a pressure is built up and the pressure is transmitted to the Bourdon tube through this capillary tube. Then it is same as applying pressure to a Bourdon tube. So, the tip of the Bourdon tube will deflect and that deflection will depend on how much of pressure that has been transmitted through this tube to the Bourdon tube. So, this tip deflection will cause a movement of this pointer against this scale, which is being magnified by this gear and linkage system. So, let us now try to break down the instrument into its various functional blocks. Let us redraw the figure here. We have the bulb of the Bourdon tube, a bulb of the pressure thermometer. Then the tube and a Bourdon tube is connected. For simplicity, let us draw a C type Bourdon tube. So, this is bulb, this is the tube or capillary tube, this is the Bourdon tube. This is gear and linkage system. This is pointer and scale. And this bulb is put to the medium whose temperature I want to measure. So, you can put to a say bath of liquid whose temperature I want to measure. So, you have the measuring medium, which is essentially this. The bulb interacts with the measuring medium and receives information about the temperature. So, the primary sensing element receives information about temperature first. And then what happens? Due to restricted thermal expansion of the filling liquid, a pressure is developed. That also happens inside the bulb. So, the temperature signal is being converted to a pressure signal. So, there is a variable conversion element. And both the functions are performed by bulb, because it is the bulb which first receives information from the measuring medium about the temperature, and due to restricted thermal expansion of the filling liquid, pressure gets developed inside the bulb. So, this signal is no more a temperature signal, but a pressure signal. Then this pressure is transmitted through this capillary tube. So, this tube works as a data transmission element. So, this is tube. I am talking about this tube, which is capillary tube. We still have pressure signal here. Then this pressure goes to Bourdon tube, which converts this pressure signal to a displacement or motion signal, because when the pressure acts inside the Bourdon tube, the tip of the Bourdon tube will deflect. So, the Bourdon tube receives pressure as input signal and gives motion or displacement as output signal. So, this is a variable conversion element. So, Bourdon tube is variable conversion element. Now, the output of the Bourdon tube is no more a pressure signal, but a displacement or motion signal. This goes to This goes through gear and linkage system, which magnifies the deflection. So, gear and linkage system works as a variable manipulation element. So, you still have motion signal, but now has been magnified. Then this signal is presented to the observer by this pointer and scale. So, pointer and scale works as data presentation element. So, finally, data is presented to observer. So, you can see here we have a primary sensing element, we have a variable conversion element, we have a data transmission element, then again we have variable conversion element, we have a variable manipulation element, and finally we have a data presentation element. Let us take another example and again break down the instrument into its various functional elements. This time let us take a very simple pressure gauge. We will take a very simple pressure gauge which measures the pressure of a fluid, and the measured pressure is indicated by a deflection of the pointer against a scale. Consider a piston here, a piston rod, and a spring here. And a pointer and scale is attached. And let the fluid pressure act on this piston surface. So, how does this work? The fluid pressure acts on the piston surface, so force will be developed. That force is transmitted through the spring through this piston rod. So, the spring gives displacement or motion as output signal, which can be used to move this pointer against this scale. So, the deflection of the pointer against this scale can be read as a measure of this fluid pressure. It is a very simple pressure gauge. So, let us now try to analyze the instrument by breaking down into its various functional elements. So, piston rod, which first interacts with the measuring medium, receives the information about the fluid pressure. So, this is of course the primary sensing element. So, we have measuring medium, which is fluid pressure here. The piston works as primary sensing element. But the force piston also converts this pressure, which is force per unit area, to force. So, piston also works as variable conversion element. So, piston is both a primary sensing element as well as a variable conversion element. So, the output from the piston is no more a pressure, but a force signal. Now, this force is converted, the force is transmitted by the piston rod. So, piston rod works as data transmission element. So, we still have force signal here. Now, this force signal is transmitted to the spring, which converts this force signal to a motion signal. So, spring works as variable conversion element. So, we now have a motion signal. This is magnified by the linkage, which is variable manipulation element. You can write it here and put the linkage here. So, we have a magnified motion, which is presented to observer by data presentation element. Which is pointer and scale here. So, data is presented to observer. So, we see it is possible to break down an instrument into its various functional elements, and the functional elements together will describe how the instrument works. Let us now move on to classification of instruments. The instruments can be classified in various ways. So, depending on the basis of classification that we choose, various instruments can be classified variously. For example, we can classify the instruments on the basis of energy consideration. That means whether it is self-operated instrument or it requires an auxiliary source of power, like whether it is an automatic instrument or a manual instrument, whether it is necessary to bring the instrument in intimate contact with the measuring medium, or it is not necessary to bring the instrument in close contact with the measuring medium. So, there are various bases for classification, and now we will see some of the ways how we can classify various instruments. So, let us start with the classification on the basis of energy consideration. On the basis of energy consideration, we can classify instruments into two categories: passive instruments and active instruments. Passive instruments are those whose output energy is supplied entirely or almost entirely by its input signal or by the energy of the input signal. So, we do not need any auxiliary source of power here. These instruments are self-operated instruments. It may be noted here that the output signal and the input signal may be of same form, or there may be an energy conversion. Some of the examples of passive instruments are ordinary mercury in glass thermometer, or a clinical thermometer, a Bourdon tube which is used for measurement of pressure, or a pitot tube. All these instruments are self-operated instruments. They do not need any power source. The energy required for the act of measurement is supplied entirely by the energy of the input signal it receives. On the other hand, active instruments are those which have an auxiliary source of power. So, they are not self-operated instruments, but they are power operated instruments. Again, the output and input signals may be of same form, or there may be an energy conversion involved. Examples of active instruments are electronic amplifier, differential transformer for displacement measurement, etc. So, this classification is on the basis of whether an instrument requires auxiliary power or not. If the instrument requires auxiliary power for its operation, the instrument will be called an active instrument. If the instrument does not require any auxiliary source of power, the instrument will be called a passive instrument. We can also classify the instruments on the basis of analog and digital mode of operation. If the instrument follows analog mode of operation, we call the instruments as analog types instruments, or if the instrument follows digital mode of operation, we call those as digital types instruments. Majority of the primary sensing elements are of analog types. They present the information about the measured variable in the form of continuous variations with respect to time. On the other hand, digital types of instruments represent the measured variables by discrete quantities or digital quantities which are discrete in nature. So, this classification is on the basis of whether a particular instrument follows analog mode of operation or digital mode of operation. Still another way of classifying instruments is on the basis of operation on a null or deflection principle. Deflection type instruments, the physical effect generated by the measuring quantity produces a similar but opposite effect in some part of the instrument, and this effect is closely related to some variable like mechanical displacement or deflection in the instrument that can be easily observed by human operators. So, the physical effect in the deflection type of instrument that is generated by the measuring quantity produces a similar but opposite effect in some part of the instrument, and this effect is closely related to some variable like mechanical displacement or deflection in the instrument that can be easily observed by an human operator. An example can be a typical spring balance or a Bourdon tube. We have just seen Bourdon tube. So, let us see the typical spring balance. So, this is a deflection type weight measuring instrument or a simple spring balance. Weight of this object is measured by the deflection of the spring caused by it. So, this is a very simple example of deflection principle. The example of boron tube we have just seen in our discussion on functional elements. Now, null types. The null types attempts to maintain deflection at 0. So, is provided with either a manually operated or automatic balancing device that generates an equivalent opposing effect to nullify the physical effect caused by the measuring quantity. These instruments are provided with either a manually operated or automatic balancing device that generates an equivalent opposing effect to nullify the physical effect caused by the measuring quantity. Examples are a dead weight pressure gauge, equal arm balance, electrical resistance measurement by Wheatstone bridge. In all these, a null point is attained during act of measurement. Let us take example of, let us say, an equal arm balance. So, draw the figure of an equal arm balance. You have unknown weight, you have standard weight. This is the null point. These are equal arms. We call this balance equal arm beam balance. The information about the weight of this unknown object can be measured directly by putting standard weights here and maintaining a null point here. Still another example can be a dead weight pressure gauge. Let us draw a simple diagram for dead weight pressure gauge. You have a platform, When the fluid pressure acts here, this will try to go up, which can be counterbalanced by putting standard weights here. So, by maintaining a null point, we can measure the fluid pressure. It may be noted here that the accuracy attainable in null method is in general higher compared to deflection method. In a null type instrument, the effect produced by the measuring quantity can be compared directly with a primary standard. As you have seen in the example of spring balance and equal arm beam balance. In case of equal arm beam balance, we are measuring the unknown weight by comparing directly with standard weights. But in case of deflection type spring balance, we are comparing the weights against the spring, but spring is not a primary standard for weights. So, in general, the null methods are superior in terms of accuracy of measurement. However, for dynamic measurements, deflection methods have distinct advantage because they are faster. However, it is possible to increase the speed of the null method by using automatic balancing devices. So, the advantage of null method is increased accuracy, but disadvantage is it is generally slow, because oftentimes it is manual. However, it can be improved using automatic balancing devices. The next classification is based on whether the instrument is contacting type or non-contacting type. As the name suggests, the instrument is contacting type when it is necessary to bring the instrument in direct contact with the measuring medium. For example, a clinical thermometer. The ordinary clinical thermometer you put in your mouth, wait for some time. How much time you wait usually depends on the time constant of the instrument, and finally you get the reading directly from the scale attached to the clinical thermometer. It is necessary for the purpose of measurement that you bring the thermometer in direct contact with the measuring medium. So, this is contacting type. Most of the instruments are contacting type. Other examples can be a thermocouple, a pressure gauge, and so on and so forth. While non-contacting types, you do not have to bring the instrument in direct contact with the measuring medium. So, the instrument can measure the variable without being in physical contact with the measuring medium. For example, an optical pyrometer or a radiation pyrometer measures the temperature of the furnace but we do not have to bring the pyrometer in direct contact with the furnace. It is inconvenient to do that as well. We will see later how this instrument works when we talk about temperature measurement in detail, but this is an instrument which is of non-contacting type. Similarly, ultrasonic level measurement, which makes use of the speed of the ultrasound to get an indication of the level of a liquid, is also non-contacting type. Let us now move on to input output configuration of instruments. We are asking here, can you develop a generalized configuration that represent significant input output relationships present in an instrument? Let us consider this general model of an instrument. An instrument receives input signal from the measuring medium and gives us an output signal which is related to this input signal. So, we can consider that there is a transfer function here which acts on this input signal and gives us output signal. Now, let us try to see what are the various types of instruments that affect this instrument, any particular instrument. The input quantities can be broadly classified into three categories: desired input, interfering inputs, and modifying inputs. Desired inputs, measurements or quantities that the instrument is designed to be measured. So, the instrument has been designed to be sensitive to desired inputs only. Interfering inputs are those quantities that unintentionally affect the instrument as a consequence of the principles used to acquire and process the desired inputs. So, the instrument becomes unintentionally sensitive to interfering input. So, while I intend to measure desired inputs and the instrument has been designed to be sensitive to desired input only, the instrument becomes unintentionally sensitive to some other inputs, and we call those inputs as interfering inputs. And finally, modifying inputs. Modifying inputs are those undesired quantities that affect the output by altering the input output relations for desired and interfering input. If we consider this as desired input and there is a transfer function which works on the desired input and gives us output. Now, modifying inputs will tend to change these transfer functions. In other words, modifying input affect the relationship that exists between input and output, and in this block diagram we are saying that this transfer function relates this input and output. So, modifying input will tend to change this transfer function if we have to speak mathematically. So, you can have a generalized input output configurations of instruments like this. We have desired inputs, modifying inputs and interfering inputs. We have a transfer function corresponding to desired inputs. So, this transfer function works on this desired input and gives us a output component due to desired input. We have an interfering input and there is a transfer function corresponding to interfering input, which gives us an output component due to interfering input. But modifying input will tend to change the relationship that exists between desired input and the output, as well as interfering input and output. So, we have a transfer function corresponding to modifying input, corresponding to modifying input versus desired input interactions, and the modifying input interfering input interactions. So, finally, we have a component for the output that is due to desired input and modifying input. We also have a component due to interfering input and modifying input. When these two signals are added together, we have the final output. We can also explain this in terms of a simpler block diagram as follows. We have measuring variables. This goes to the input instrument or sensor. So, this is the desired input. It also receives interfering input as input signal and also modifying input as input signal, and finally gives us the output. As I was telling you that modifying input will tend to change the relationship between this output and these two inputs. It can be explained graphically like this. Suppose this is the input output relationship when there is no interfering input, when there is no modifying input. In presence of modifying input, this relationship can be shifted like this. So, we will stop here for the day, and in our next class we will see more on interfering input, desired input and modifying input, what corrective measures we can take so that our instrument is sensitive to only desired inputs. In other words, how can we cancel out the effect of interfering input and modifying input.